Our final lesson in Chapter 6 is solving radical equations. We're going to use properties of exponents to solve, and we check for what's called extraneous solutions. Now, when we used to solve equations that were quadratic, something like x squared is equal to 25, we would solve by taking the square root of each side, and we recognized that we had two possible solutions, plus or minus 5. But when we solve a radical equation, we have to be careful with the type of index. If you have a square root of a value equals a number, then you square each side, we get 36. So we only get one solution this time. So we have to think about checking some solutions to make sure they're not extraneous, and I'll show you what that looks like down below. When asked to solve a radical equation, we're going to isolate, raise, and solve. So what I mean by isolate is isolate the radical to one side if necessary. If anything's being added or subtracted on the outside of the radical, move that over first. Then we raise each side to the same power to eliminate the radical. So think about the index of the radical, and that's the power we'll raise it to. Then we solve what's left over. So once you get rid of the radical symbol, isolate your variable. So here's what I mean about checking for your solutions. If your index is odd, like a cubed root or a fifth root, all solutions are possible. And we talked about that at the very beginning of the chapter. But if your index is even, some solutions are not possible, and those are called extraneous. Here's what that will look like. An extraneous solution is when you get a value for x that makes the equation false when you plug it back in. So watch what happens here. If we take the square root of x and set it equal to a negative number, technically, to get x by itself, we square each side. The squared cancels out, and we have x equals positive 9. But when we check something like that, because we had an even root, the square root of 9 can only be a positive value. It can't have that negative output to be a function. So even though solving a quadratic would give you plus or minus, solving a radical can only give you plus. So this is not a valid solution for the square root of positive 9. I know it seems kind of tricky, so it's different than solving a quadratic. The square root of 9 is just 3, and 3 doesn't equal negative 3. We only have to check it if we have an even index. You're going to want your properties of exponents. You're going to want to know how to FOIL when necessary. We maybe need our factoring rules from Chapter 4. And at the very least, we could possibly use the quadratic formula. So let's solve some radical equations. Our first one, the cubed root of x minus 9 equals negative 1. I know this is a really big looking equation. I'm not quite sure why I put it on there like that, but it is what it is. If we have the cubed root, that means the index is 3. This indicates all solutions are possible. Step 1, isolate the radical. We want to get this term all by itself. To do that, I'm going to add 9 to the other side. That leaves us with the cubed root of x, and on the right, negative 1 plus 9 is 8. Now you want to raise this side, or each side, to the same power as the index, which means I'm going to cube that left-hand side and cube the right-hand side. The cubed and the index of 3 cancel out, leaving you with just x. On the right, 8 to the third power, or 8 cubed, is 512. And again, because the index is odd, this is a valid solution. It's not extraneous. Over on the right, we have an example that is an even root. So let's see how this works. We have the square root of x plus 25 is equal to positive 4. So notice the x, or the radical, is by itself. Even though the 25 is on the inside, nothing's being added or subtracted outside of it. So what we're going to do to get rid of that radical is square each side. Cancels out the index and gives us x plus 25. Now on the right, 4 squared is 16. To get x by itself, I'm going to subtract 25, to move that over. And we get x is equal to negative 9. So we do need to check that. When we check even roots, we'll substitute that back in for x in the original equation. Negative 9 plus 25. Is it valid that it'll equal positive 4? Well, negative 9 plus 25 is positive 16, and the square root of 16 will be positive 4, so that one checks as well. When we get a problem that has an x on each side of the equation, we want to make sure that we follow our appropriate rules. We have x plus 1 equals the square root of 7x plus 15. So your goal is to isolate the radical. Notice on that right-hand side, 7x plus 15 is on the inside. That means the radical is isolated. To get rid of the index, we're going to have to square each side. Now, when we square the left-hand side, notice it's x plus 1 on the inside. We have to think FOIL here. We've talked about this a lot, so we have to remember that rule. If there's addition or subtraction, and you square it, you have to write it out twice in FOIL. On the right-hand side, the index and the power cancel, giving you 7x plus 15. If we FOIL x plus 1 times x plus 1, we get x squared plus 1x plus 1x plus 1, which is x squared plus 2x plus 1, equals 7x plus 15. We've changed this problem from a radical equation to a quadratic equation. And we know that because we have an x squared term in the equation. Because of that, we have to set everything over to, or move everything over to one side to actually set the equation equal to 0. Oops, I don't know why I did that over there, sorry. So I'm just going to scroll up a little bit. If we move everything over to the same side, I'm going to take 7x and subtract it and line it up right underneath the 2x. Take the 15 and subtract it and move it right underneath the 1. Combining like terms, we would have x squared minus 5x minus 14, and on the right it equals 0. To solve this quadratic equation, we would either try to factor or we could do quadratic formula. Notice the number in front of x squared is just a 1, so that means we just need to split that constant, negative 14, into two numbers that would possibly multiply to get negative 14 and add to get negative 5 at the same time. If we pick 7 and 2, as long as the 7's negative, they'd multiply to get negative 14 and add to get negative 5. That means x squared minus 5x minus 14 is factorable. X squared would split up into x times x, and we'd have minus 7 and plus 2. Now, applying the zero product property, if we set x minus 7 equal to 0, a possible solution for x is x equals 7. And if we set x plus 2 equal to 0, another possible solution for x is negative 2. Going back to the original problem, though, remember the index is 2. It's even. That means we have to check for extraneous solutions. When we plug in these values, we need to make sure that our square root has a positive output on the right. I'm going to test 7 first. I'll just plug in 7 where I see x in both parts of the equation. 7 plus 1 is equal to the square root of 7 times 7 plus 15. Well, 7 plus 1 is 8. 7 times 7 is 49 plus 15 is 64. The square root of 64 is 8, and 8 is positive, so that's a valid solution. But watch what happens when we test negative 2. If we plug in negative 2 for x on both sides, Negative 2 plus 1 is negative 1 on the left. And we have negative 14 plus 15 on the right. And that would be the square root of 1. Well, the square root of 1, in order to be a function, again, has to have that positive output. And positive 1 doesn't equal negative 1. So that means that that's not going to work, which means x equals 2 is extraneous. It solved our quadratic equation, but when we plug it back into the radical, it doesn't work. That means 7 is the only solution. Before we end the video, for some reason the last part of the notes for 6.6 didn't make it onto your packet. We are going to add this last little section on this page and then we'll be done. For whatever reason, this didn't end up in your packet, and I'm not quite sure why. But I do want you to write this down and then kind of keep following along. To solve with a rational exponent instead of a radical, we're still going to isolate, raise, and solve. We're going to do those same steps. This time you want to get your base by itself on one side. So remember, the base is the part or the term that has the variable. Sometimes you have to add and subtract to move things over, and then sometimes you might have to divide to move something over. Then you want to raise each side of the equation to the reciprocal exponent to eliminate the original one. Solve from there, and then check your solution. Please write all that down, and then when you're ready, press play, and we'll continue. In our first example, we have 9 times x to the 3/5 power equals 72. Notice the 9 and the x are not in the parentheses. That means the base is just the x. So we have to get rid of the 9 first. So we're going to, step 1, we want to isolate the base. We'll divide both sides by 9. It cancels out on the left. That gives us x to the 3/5 power. On the right, 72 divided by 9 is positive 8. Then it says raise each side of the equation to the reciprocal power. So this is a great opportunity to recognize not to write your exponent with a diagonal fraction bar like it's written in the beginning. You should write it top to bottom like I wrote it in pink in that second row. And that way when you raise it to the reciprocal power, you're going to raise it to the 5/3 power. That would be the reciprocal of 3/5. If you do that on the left side, we'll do that on the right side. Raise it to the 5/3 power. And the purpose of doing that, with the original exponent, the 3's would actually cross off, and so would the 5's. And that's how you get x by itself. On the right, we're going to evaluate this using the powers chart. If we have 8 to the 5/3, that's the same thing as saying the cubed root of 8 to the 5th power. So in your perfect cubed column, the cubed root of 8 is 2. And if we raise 2 to the 5th power, go to that 5th powers column, we get 32. So x equals 32. And that should be a valid solution. One other thing to talk about to check your solutions. If your exponent is m over n, if n is even, that's when you have to check for extraneous, because that means you're taking an even root. I guess I forgot to say that before. Sorry about that. So in this case, notice your root is 5. That's odd. So we're good to go. That would be a valid solution. For our last example, we have x plus 2 to the 3/4 power minus 1 is equal to 7. When we think about what's happening here, our exponent is with a parenthesis, meaning x plus 2 is the total base. So we want to get that by itself first. We'll have to do that by moving 1 to the other side. And that gives us x plus 2 to the 3/4 power. That's a 4 right there. There we go. On the right, 7 plus 1 is 8. Once you isolate the base, raise each side to the reciprocal power. So I'm going to go 4/3 on the left and 4/3 on the right. And again, the purpose of that, with the original exponent, the 3's cancel and the 4's cancel. And that means we can eliminate our parentheses and have x plus 2 by itself. On the right, if we take 8 to the 4/3 power, That's the same thing as saying the cubed root of 8 to the 4th power. The cubed root of 8 is 2, and 2 to the 4th power is 16. Finally, to get x by itself, move that 2 over, and we get a tentative solution of 14. But because our denominator of that rational exponent is even, we want to double check this. So we're going to do a little verify here. If I plug in 14 for x and raise it to the 3/4 power minus 1, will we get 7? Well, 14 plus 2 is 16. 16 to the 3/4 power means the 4th root of 16 cubed. The 4th root of 16 is 2. 2 cubed is 8. And 8 minus 1 does in fact equal 7. So x equals 14 is a valid solution. And that's the video lesson for 6.6.